In this video, we're going to talk about the shapes of simple molecules and ions. We'll talk about each individual shape and some examples of those, and make sure you can answer exam questions and get all of the marks. This is based upon electron pair repulsion theory. So we need to know how many electrons are around the central atom in a molecule. And we need to then determine the angle between those electron pairs and the name of that shape. So this theory states that the shape of a molecule depends on the number of electron pairs. That's the number of electron pairs surrounding the central atom. And those number of electron pairs separate out themselves as far apart as they can because they're negative and they repel each other. So in order to determine whether or what the actual angle is, you'll need to be able to draw out, and that's our exam tip, draw out and recognise the pairs of electrons in molecules and ions. So you have to draw these things out. So we're going to draw a few of these things out to make sure you understand. Now these two parts are in green because they are required when you explain a bond angle. So if you have a question that says explain the bond angle, you must quote the number of electron pairs, whether they're bonding or lone pairs, okay? And you must say that they repel each other as far apart as possible. So it's really important you remember those two things. Each bond angle we go through, I would, if I was you and I was watching, I would look at it and say, well, can I do that before? And you can skip to the different ones to remind yourself as you go through the video. The first one is tetrahedral. So that has a number of bonding pairs of 4. And most common example is alkanes. And it has a tetrahedral shape of 109.5. So the bond angle between the electrons is 109.5, and you have to memorize that. It's the most important thing. Let's look at a couple of examples. The first one is CH4. So we know from CH4, we know that the carbon is surrounded by, there you go, 4 hydrogens. Then if we put the electrons in, you can see if I put the hydrogen electrons in there's my hydrogen electrons. And then I go from my hydrogen electrons to my carbon electrons. And like I say, you should be trying to draw this out, maybe even pause the video, try and do it before I do. Okay, and there we have bonding pairs. They are between atoms. Okay, so any pair that is between an atom, okay, or between atoms, sorry. So this is between the H and the C, that is involved in a bond, okay, and that is a single bond. So one pair of electrons is a single bond, which hopefully you're used to. If that's the case, we have 4 bonding pairs, they're all bonded. So let's draw this in a slightly different way. So if I'm determining the bond angle, I can quickly go, there's 4 bonding pairs and therefore it's tetrahedral, therefore it's 109.5. So the angle between these is 109.5. But if you're drawing the shape, so it's really, really important, if you're drawing the shape, you have to do the following. So you have to do it in dash and wedge. So the same thing, we will draw out the bonds and single bonds, because these are all pairs of electrons, so they're single bonds. And we're going to draw out let's go for it. There you go, there's a wedge. And there's a dash. And then we draw out 2 single bonds. Okay, so we have got 4 bonds in total. 1, 2, 3, 4 bonds, and we know that we've got a dash, we got a dash and we've got a wedge. Now just explaining the dash and the wedge. The wedge looks like it's getting bigger as it comes to you, so that looks like it's coming towards you. So that is coming out of the board. Okay, so for example, if you're standing, it's coming towards you. Okay, from where I'm standing, it's coming towards me. But where you're standing, it's coming towards you. This one is going away. So again, relative to where you are, that's going into the board or into the video, essentially. So that means that we have a 3D shape. So a 3D shape. And if you're in a lesson or anything like that, I'd recommend you build it and you can really see it at that point. If we then put are hydrogens on the end of these bonds. Okay, we have our 3D diagram of the whole thing. Now, if you're drawing the shape, they often ask you to label the bond angle. So the bond angle is the difference between where these two bonding pairs are. And it's all the same bond angle, so we'll have 109.5 here, 109.5 here, 109.5, 109.5. And then you have to label it as 109.5 degrees, okay? So that is our bond angle in terms of tetrahedral. Now, tetrahedral can happen in anything that has 4 bonding pairs. So our next example, CH2ClF. Now, I'm not going to draw all of the electrons out. I'm going to go straight to the shape. So let's practice drawing that shape again. So this time, we know it's got 4 bonding pairs. So what I'm going to do is I'm going to put C on. Okay, and again, I do my dash and wedge, or wedge and dash. And there you go. And get very much used to just drawing those out. And then this time we've got 2 H's, so let's just put 2 H's on. There's my H's, and then it's a Cl and an F. So Cl and an F. And again, we've got 4 bonding pairs, and get used to seeing these bonds. If you see bonds, single bonds, it must have a single pair of electrons in there, 1 bonding pair, so they'll go 1, 2, 3, 4 bonding pairs. Okay, if it's got 4 bonding pairs, the bond angle is going to be, as we've said already, tetrahedral, 109.5 degrees. And there's your 2 examples of tetrahedral and 109.5 degrees. The last tricky example of tetrahedral is actually going to be with regions, so number of bonding regions. And this is the most difficult question and one which people struggle with. So you can actually have tetrahedral if you have bonding regions. And remember, bonding regions means more than 1 pair of electrons, so it might be 2. So examples are sulfate and phosphate, okay, and they're 109.5 tetrahedral, as we've done. So if you look here, we have got 2 bonding regions that are double bonds, okay, and then 2 single bonds. But in total, it's 1, 2, 3, 4 bonding regions, therefore tetrahedral. Look at the other one, look at phosphate. Again, a double bond here. As soon as you see double bond, you can say a bonding region. So 1, 2, 3, 4 again. And because of that, that means this is tetrahedral. And we've added this to the video. As you can see, I'm wearing something different. They look a bit different because this is the super hard bit that we missed off. So therefore, bonding regions, 4, okay, come across these examples, tetrahedral all day long. Now, in this example, we have 3 bonding pairs and 1 lone pair. So lone pair is where it's not bonded. It's just in the outer shell, not bonded to anything else. Okay, so our exam tip here is based upon those lone pairs. Lone pairs repel more by an additional 2.5 degrees. So they repel. So what they do is imagine there are 2 electrons right here, and there's a lone pair sitting here at the top. It will repel the electrons and then just push them slightly down that way. That reduces the angle between the electrons by about 2.5 degrees, okay? Because the electrons, the lone pairs, are not shared, so they repel more. Okay, so let's look at an example, okay, of this pyramidal shape. Now the pyramidal shape is 107 because if you think there's 4 pairs, would be 109.5, but of the 4 pairs, 1 is a lone pair, so it's reduced this angle by 2.5. So 109.5 take away 2.5 is 107. So this one is 107. Now we're going to do 2 examples. And the 2 examples that we're going to do are the most simplest one that you'll come across, which is NH3 to start off with, and we'll do an amine as well. Now if we look at NH3, again 3 H's around it. And if we do our electrons on there, so we'll do our 5 electrons from our nitrogen. Okay, there we've got our 5 electrons from our nitrogen. Okay, and we will have our electrons from our hydrogens there. So this is 3 bonding pairs. But this bit here is our lone pair. Okay, which is our lone pair. So we have got 1 lone pair, as said here, 3 bonding pairs. Okay, if you ever see that setup, it's going to be 107 pyramidal shape. Okay. If you're drawing this, you might do the same thing that we've done in the last one, and you draw the shape. Remember, if they ask you to draw the shape, it's really important that you do the following. Okay, and you can draw it in a similar way. So you can go, there's my wedge, and there's my dash, and you'll often see it like that. And I'm going to put my lone pair of electrons up here because my lone pair of electrons is not involved in any bonding whatsoever, and I'll put my H's on the end there. Okay, and this is the kind of shape you're seeing. So this angle, this is where I'm labelling the bond angle, is going to be 107. Okay, so 107. And that's how you draw a pyramidal shape. And this is how you find out the number of electrons or bonding pairs. So we have 3 bonding pairs, 1 lone pair, 107 degrees. Now the example that comes up, has come up in a A-level examination, is that of an amine. And it doesn't look quite the same. So this is CH3 NH2. So CH3 NH2, if you look at the bonding, is going to be C, and I'm going to draw it slightly differently here. It's going to be bonded like this, and you might be used to drawing it in this way. Okay, and you have, that's your CH3 NH2, an amine called methanamine. So if you look here, and we look at this angle here, so you see it's around the central atom. If you have a central atom, you'll have an angle between the bonding pairs. So if we look here, instead of drawing out these electrons and having to do that every single time, we can look at bonds instead. So we can say, right, okay, there, single bond, that's a bonding pair of electrons, bonding pair of electrons, bonding pair of electrons, bonding pair of electrons. 4 bonding pair of electrons, therefore the angle between here and here is going to be 109.5. Okay, so that's 109.5 because I have 4 bonding pairs. If we then look at this one, we can say, oh, there are 3 bonding pairs because I have 3 bonds. But this time I have to draw out the full number of electrons because otherwise I will not see my lone pair. But there is a lone pair here. So this is where you might have to do this diagram, draw the electrons out. But often you can see it here, and you get used to seeing the lone pairs on it. You see I've got 3 bonding pairs, 1 lone pair. So the angle between here and here is going to be 107 degrees. So we have a pyramidal shape and we have a tetrahedral shape, all in the same molecule. And I would encourage you, if you're going to practice, is just look at molecules which have lots of different bond angles within them. The next angle we're going to discuss is the nonlinear or bent angle, sometimes also known as angular. That has 4 pairs of electrons, which consist of 2 bonding pairs and 2 lone pairs. Now we know from our exam tip before that lone pairs repel by 2.5 degrees more, but we have 2 lone pairs. So therefore the bond angle is reduced by 5 degrees because 2.5 times 2 is 5. But we need to know what is the original bond angle. The original bond angle is based upon the 4 pairs of electrons. If you go back, you'll see that 4 pairs of electrons is a tetrahedral shape. So tetrahedral is 109.5. So if we take the 5 away from 109.5, we get 104.5. So 104.5 is our angle for non-linear. The example of this, which is most commonly used, is water. So if you draw water, water has 2 bonds here. Okay, and then we put the electrons in for the hydrogens. There's our hydrogen electrons. Okay, and then we put in our oxygen electrons. and there's our oxygen electrons. And you'll notice that we have 2 lone pairs and we have 2 bonding pairs. If we then put the bond angle on here, we say, right, what is the bond angle here? It'd be 104.5 degrees. And that's how you draw the bond angle for nonlinear for water. There's another example, though, we can talk about that might occur more often because water is the easiest example and won't come up as often, okay, which is if we're talking about methanol. So if we're talking about methanol, this is our methanol drawing. And we again put all our electrons on. So I'm going to put, there's a dot there, there's a dot there. There we go. Okay, we put it simply like this. We're putting then our other sets of electrons on. So there we go. Okay, you notice there are 4 pairs of electrons around that central atom, which means that the angle there between there and there would be 109.5. So that'd be 109.5. But there is an angle that goes from here to here. So if that is the case, something really important to notice is we've just drawn all the electrons on for the single bonds. That's all we've done. Okay, but we know there are 8 in the outer shell. We also know that oxygen has 6 electrons and hydrogen only has 1. We know carbon has 4. So I've drawn my 4 carbons, electrons. Okay, but have I drawn my 6? No, I haven't drawn my 6 for... Now, if you're drawing this as a proper diagram, you would probably do crosses, dots, and triangles and different options. I'm just doing this simply here just to show you the bonding pair, so I'm not really bothered about whether each atom has a different shape, but normally you would draw them each with different shape. But what we can see here is that there's 2 lone pairs, 2 bonding pairs. So this angle here is 104.5 degrees. So in methanol we have a non-linear bond angle and we have a tetrahedral bond angle. So you can have, when you're in the exam, easily molecules that have 2 different bond angles in them. So get used to doing those type of questions. Our next bond angle is octahedral. Okay, the most common example of octahedral is SF6. So the important thing here is that you know you've got 6 fluorines next to 1 sulfur. And the other important thing is that this does not obey the octet rule. So if I'm doing an S, what we need to do is then realise that if there's 6 fluorines, all I have to do is put 6 fluorines around. And there you go. That's 6 fluorines around. Now 2 of those fluorines are in the plane of the board. Okay, so they're in the plane of the board, they're flat. Okay, 2 of the fluorines are coming out at you. Okay, and they're coming out at you. And then 2 are going away from you. And you have this SF6. Now each one of those is 2 electrons. So 2, 4, 6, 8, 10, 12. So it has 12 electrons in its outer shell. Because it has 12 electrons in its outer shell, it doesn't obey the octet rule, so some people can get confused. Okay, but phosphorus and sulfur tend to do this quite often. If that's the case, the bond angle between them is 90 degrees. So every single fluorine is 90 degrees. Really good if you have the chance to make a model of this and you can actually see it in real life. But for now, all I can do is draw it for you. So 90 degrees between every single atom on there. We're now going to talk about 2 further angles which are both planar, which are both flat. So the first one is when you have 2 bonding pairs or regions of electrons each side of the atom. Now that is called linear, and that is 180 degrees. So another angle, linear 180 degrees. Now, two examples of linear, which are the most common, is when you have examples with beryllium, and we have beryllium chloride here. Okay, and if you have beryllium chloride and you draw the electrons, beryllium is in group 2, so therefore I'm going to draw 2 electrons for beryllium, and I can just draw 2 electrons because there are 2 single bonds. So I can draw single bonds, have 1 pair of electrons in, so I can just draw those on. All these other electrons in chlorine I don't have to worry about because they're not around the central atom, and so therefore they don't create the bond angle. So this fits the definition, two bonding pairs, so I've got 2 bonding pairs, and therefore that is 180 degrees. If I then switch that to bonding regions of electrons, I can do carbon dioxide, and this often happens with other things like carbon disulfide and things like that, which they can complicate it with. If I put the electrons in, I know that I've got 2 pairs of electrons there, so one each from the carbon, and then and there you have all of your electrons in the carbon dioxide. So that means this will now be known as a bonding region of electrons because it has more than 1 pair of electrons in it. So I have 2 bonding regions of electrons, and therefore again the bond angle will be 180. That is as far apart as they can possibly get, which goes back to our theory at the start, electron pair repulsion theory. They can get as far apart as possible as 180 degrees. And the reason they're flat as well is because they're restricted in rotation. Okay, and you'll talk about that when you do alkenes as well. The double bond restricts the rotation, therefore this is flat, planar, okay, and this is also planar, but this time because it has only 2 pairs of electron each side of the atom. Our next bond angle that is flat and planar is trigonal planar. So trigonal planar is 120 degrees, and it's 3 bonding pairs or regions essentially. So 3 regions of electrons or 3 bonding pairs of electrons. I've done this a little bit quicker here, and you see over here I have got, you may recognize this as an aldehyde. This is methanal. You can see there are, again, we're doing it a little bit, we're not drawing all the electrons on now because hopefully we should start to be able to do it without drawing all the electrons on if we recognize the number of electrons in bond. So I know there are 2 bonding pairs here, so this is a bonding region, 1 bonding pair here, 1 bonding pair here. So I've got 2 bonding pairs and 1 bonding region, which means in total I have 3 bonding regions, I can call it in the exam, and therefore I've got 120 degrees between these. Now the reason it's 120 degrees is because this is fixed because of this double bond. So this double bond fixes the rotation. It can't rotate anywhere, it's flat. Because it's flat, you can consider the whole angle as 360, and there are 3 different things, so 360 divided by 3 is 120. Another example that you're going to come across is any alkene. So an alkene, again, restricted rotation here. And because there's restricted rotation here, it stays flat. Okay, and you've got that 120 degree bond angle again. And then we have benzene. So this is cyclo 135 hexatriene, or benzene. And you can see there's a double bond here, restricted rotation. There's a hydrogen you cannot see. So there are 3 bonding regions around there, and therefore 120 degrees. Now there's one last one that is sent to confuse you, which is trigonal planar, which is BF3. So BF3, very similar to the other ones, but this time the reason is that there are 3 bonding pairs of electrons. So 1, 2, 3 bonding pairs of electrons. 3 bonding pairs of electrons, that is still going to be 120 degrees. Okay, so they're your common examples of planar molecules, and specifically trigonal planar, 120 degrees, 3 bonding regions of electrons or 3 bonding pairs. We're now going to look at ions and how to recognize bond angles in ions. Now normally the ions include an extra electron or missing an electron. They don't get any more complicated than that. The first one we're going to do is going to be this ammonium ion. Now ammonium is normally presented to you as NH4+. Now, but ammonia, if we put the hydrogens on and we start putting our electrons in, we can see that there are 5 electrons coming from the nitrogen. There's our 5 electrons from the nitrogen, and then we'll put our hydrogen electrons. Now, ammonium comes from ammonia, which is NH3. So if I say NH3 plus H+. So if you join those two together, you will get ammonium. So if you get ammonium that way, that hydrogen has no electrons at all. Okay, and what it does a dative covalent bond. So if you may have seen this in another video, but this is a dative covalent bond. That means where both electrons come from one atom only, and that's from the N towards the H. Okay, so the whole thing has a positive due to that fact. It's having a proton added to the NH3. Now that means this is now a shared pair of electrons. Okay, so it's now a bonding pair. So we have 1, 2, 3, 4. So we have 1, 2, 3, 4 bonding pairs of electrons. That means the angle from there to there, 4 bonding pairs of electrons, will be 109.5 degrees, and it will therefore be tetrahedral. Okay, so that will be tetrahedral. If we then look at our next example is NH2 minus. So NH2 minus, if we draw it out again, now NH2 minus is going to be those 2. There you go, and we can put our electrons all the way on the top. So let's do our nitrogen electrons this time. Okay, sorry, our hydrogen electrons first. And let's do our nitrogen electrons now. 2, 3, 4, 5. So I've got my 5 electrons from the nitrogen. I've got 2 electrons from the hydrogen. Okay. Now, if that is the case, it's a minus ion. So whereas this was positive, this is negative. So it must have had an electron gained from somewhere else, which I've drawn as a triangle. If that is the case, you then look at all of these and say, right, okay, I've got now 2 bonding pairs and 2 lone pairs. So this is not bonded with anything else, it's just an added electron. We've now got 2 lone pairs, 2 bonding pairs, 2 lone pairs, 2 bonding pairs. Hopefully you can remember, is 104.5 degrees, which means you will have non-linear. Okay. So there's 2 examples of where you can draw ions to find out the bond angles. And it's important with these ions, as you can see, draw the electrons, recognize the electrons. You don't always have to draw it if you're really good at recognizing, but it is a really good tip to draw the electrons if you're in the slightest bit not sure. So finally, it's good to put this all together in an explanation question. So state and explain the shape and bond angle in hydrogen sulfide. During this question, you must look at the number of electron pairs and describe why the repulsion exists. So let's quickly just draw this, just to give us an idea of what we're dealing with. So we have S. There you go. Let's draw our electrons out. So we have 6 in our sulfur, and we have 1 each from the hydrogen. So let's draw our sulfur first. So 1 will go because that's the pair of electrons there. There we go. There's our 6 electrons in our sulfur. And then let's draw our hydrogen electrons on there. So that's the first thing I would do if I was in the exam. Let's draw that and let's see what the actual answer is now going to be. So first of all, we can see it's got 2 lone pairs of electrons and 2 bonding pairs. So that is nonlinear 104.5. Okay, we have to state that there are 2 bonding pairs and 2 lone pairs of electrons. We have to say that the lone pairs repel by 2.5 degrees more than bonding pairs. So each one of these is mark worthy, okay? So make sure you do them. And then the last bit is the electron pairs repel each other so they are as far apart as possible. So all of these could potentially get you a mark in the exam. So make sure if you're doing any type of bond angle, state and explain the shape. Make sure you do that. And importantly, draw the electrons if you're not sure as well.